Hope you paid attention the first 14 slides. So all of our gases in a mixture have the same volume, and they all have the same average kinetic energy. Therefore, in certain applications, you can think of a mixture of a gas as one gas because of these properties. So even though air is a mixture, we can measure the pressure, volume, and temperature of air as if it was a pure substance, because all of the air molecules have the same volume and the same average kinetic temperature. We can calculate the total moles of a molecule in a sample of air if we know PV and T, even though they're different molecules. Now, we might have a different amount of moles of each gas, but we can figure that out. Now, even though volume is going to be the same, we do have to consider pressure. So the pressure of a single gas in a mixture of gases is what we call its partial pressure. And pressure is going to be additive. Volume's not. Volume's always equal, but pressure is. So we can calculate the partial pressure of the gas if we know what fraction of the mixture it composes and its total pressure. So, or if we know the number of moles of the gas in container of a known volume and temperature. The sum of the partial pressures of all the gases in a mixture equals to our total pressure. That's Dalton's law of partial pressures. All that says is all the partial pressures are additive to the total pressure. That's all we're thinking about. So let's say we have 3 gases in a sample. The partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C is going to be equal to the total pressure. If we have 50 gases in a sample, then that's still going to be true, but you have 50 partial pressures. I won't give you one with 50, but you should be able to do these partial pressures. Now, the gases do behave independently. They don't have interactions between each other. That's why we can say the volume is equal to all of them, because each gas just takes up the space of the container it fills. So let's look at some equations, but it's really just PV equals nRT. So for 2 gases that mix together, A and B, pressure of A is going to be equal to moles of A times R, T, and V. And remember, V and T are the same for everything in the mixture. So the only thing that's different is the amount of moles and therefore the pressure. PB is going to be equal to the amount of moles of B times RT divided by B. This is just your PB equals nRT, but we're breaking it up by our different molecules. If we had a C in there, we'd have the same type of equation. The temperature and volume of everything in the mixture are the same, so this number is going to be the same whether we're finding PA or PB if they're in one mixture. So if they're in one container. And our total moles of our 2 gases that are mixed are going to be clearly additive of mole A and mole B. And our total pressure is going to be additive of PA and PB. So let's say we have a mixture, and I know my total pressure, and I know my moles of one of my substances. And of course, I know temperature and volume. I can calculate my pressure of A, I can calculate my pressure of B. So I just need to know a couple of things and I can figure out everything else. Again, remember, volume and temperature is the same for both gases. And of course, my P total is equal to my total moles times RT over V. So that's just my PV equals nRT. But I need my total moles to get my total pressure. Because remember, the amount of moles affects the volume, and our volume staying the same, so our amount of moles affects our pressure. The more moles you have, the higher your pressure. So each of our gases have an independent amount of moles, and our total pressure depends upon our total amount of moles. So if we know a couple of these things, we can do some calculations. Now again, volume, temperature here is in the correct units, and so is pressure. But watch out, you will have to do calculations if they're not in the correct units, just for time constraints. I'm not going to keep on converting. You should be able to do that. And remember, I will give you the conversion chart for pressure. You should know how to convert temperature. You should know how to convert volume from something like milliliters to liters. So here we want to know the partial pressure of neon. It's relevant that it's neon for this discussion. In a mixture, we don't need to know what else is in there. But we do know the total pressure at 3.9 atm. We know our volume and our temperature. And we know our moles of Xe. So apparently we have a mixture that contains Xe. This particular question isn't as clear as I would make mine. We're assuming that we must have a mixture with just neon and xenon. Otherwise, we wouldn't be able to figure this out. So we need to know some things like, if not exactly what's in the mixture, but at least how many types of gas are mixed in there. So we know our moles of one of them, and we can do this calculation. Now, there's multiple ways you can go about doing this, and they're going to lead to the same answer. So we're trying to find our pressure of neon, but we have our total pressure. So there's two ways you can really go about doing this. You can find your total moles, because you do have your total pressure, and then you have your moles of xenon, so you can calculate what your moles of neon would be. And then you can calculate its pressure. Or you can go through the way I'm going to go through, which is find your pressure of xenon and then just subtract that from your total pressure. So I'm only using PV equals nRT once, but you can do it both ways and you'll find the same answer. Because really there's one thing we are looking for, which is the partial pressure of neon. So there are multiple ways you can go about doing this. I'm going to go through what's maybe a little bit simpler of a way, but they both work. So just keep that in mind. So if I know my total pressure, and I know that my pressure of neon plus my pressure of xenon is going to be equal to my total pressure, if I find my pressure of xenon, then I can figure out my pressure of my other mixture in the sample. So that's the way that I'm going to go through this. I'm going to find my pressure of xenon, and then I know my total pressure, I know my pressure of xenon, so I can use this equation that my P total is equal to PNE plus PXE, and find my PNE. That's one way you can do it, and this is just slightly easier because I'm only using PV equals nRT once. But again, you could figure out your moles of xenon. Using your moles, figure out your total moles, and then do that calculation. But it's a little bit more work. So our first step is we need to know our pressure of xenon. We have our total pressure, but we have these two unknowns that we don't know, but we have a way to find y. So that's our first step. We're going to find pressure of xenon. So our pressure of xenon is going to be equal to our moles of xenon, which we were given, times R times T over V. And we have T, we have V, and of course we have R, we always have R. So 0.17 moles of xenon times R times our temperature, of course, and that's in Kelvin already, so we don't have to do a conversion, divided by our volume, which is in liters already, so we don't have to do a conversion. So that'll leave us with our partial pressure of xenon, we know our total pressure, so I can plug that in. That was given to us as 3.9. Now clearly, if this number had come out bigger than 3.9, I did something wrong. Because my partial pressure can't be more than my total pressure. So if that had been the case, I'd know that I did something not quite right. So we're looking for our pressure of neon. And we just calculated our pressure of xenon. So we can solve for that. again, the partial pressure of neon should not be more than our total pressure. If it is, you did something incorrectly, because our total pressure should be the highest pressure. Let's look at another example. So here, we're taking 1 liter mixture of helium, neon, and argon. And that's HAS, not AHS. I don't know. It's a typo. And we know the total pressure at 298 Kelvin. And we're also given the partial pressure of helium and the partial pressure of neon. Now notice those partial pressures are in millimeter mercury. So we can't really compare millimeters mercury and use our PV equals nRT. That has to be converted to ATM. But since they're all in millimeters mercury, you can do all the conversions from ATM right off, or you can figure out the partial pressure of what we're looking for, which is argon, and then calculate it to ATM. Because you can add like units, so that just saves you a little bit of time, but you can do all of the conversions right away. So we know our total pressure, and we know our partial pressure of 2 of the gases in the mixture. So we can figure out our partial pressure of argon, and then it wants to know the mass of argon. But we can do that because we can figure out our moles using PV equals nRT if we know our partial pressure of argon. Once we know our moles, we know our molar mass of argon. We can look it up on the periodic table, so we can calculate our mass. So don't let the fact that we're asking for mass confuse you. If you know the moles of a substance and you know the molar mass of the substance, you can figure out the mass of the substance. So don't let the fact that mass is what we're looking for trip you up. So what are we going to do? We are first going to calculate our partial pressure of argon because we know our total pressure is equal to our partial pressure of helium, which we're given, plus our partial pressure of argon, plus our partial pressure of neon. And we're also given the partial pressure of neon. So as long as we know those three things, we can calculate our partial pressure of argon. And like I said, you can convert to ATM first, but I'd rather just do 1 conversion than doing 3. So I'm going to convert after I figure out my partial pressure of argon in millimeters mercury. So when I calculate that, I find my partial pressure of argon to be 209 millimeters mercury. But we must convert that to ATM, otherwise we cannot use our gas equation because of R. So we want to convert to our atomic mass units. And again, these conversions will be provided to you, but the more you practice, the more you'll remember that 760 is your conversion for millimeters mercury. So once we have our partial pressure of argon in our ATM, now we can figure out our moles. Because again, we know PV equals nRT. So we know our moles of argon is equal to our pressure of argon times volume over RT. All I did was rearrange that equation. This is not a new equation. This is the same equation that we've been using. The only difference is now we're breaking it up with our partial pressures. So we can figure out our moles of argon very easily by using our partial pressure. So we just figured out our partial pressure, and we converted it to our correct units. We know our volume is 1 liter. Remember, that's the volume for our total volume. That's always our volume. Our volume is 1 liter for all gases. Our R doesn't change. And our temperature is not going to change either. And that's already in Kelvin. So when we do that calculation, we find our moles. So the last step, now that we have our moles, and again, we should really only have 3 significant figures, and we do, but this wants to know our mass, and that's really easy because we know our molar mass. So if you look up on the periodic table, our molar mass of argon is 39.95 grams per mole. So we have our moles argon so we can figure out our mass of argon in our sample. Again, don't let the fact that it's asking for mass confuse you. You know how to do that. You have converted moles to mass. You could convert moles to molecules as well using Avogadro's number if you needed to. So you can do a lot of things once you know the moles based on what we've talked about previously in our classes. Oh, that's just the same thing. So I'm going to stop it here, and I have a quiz for you. Nothing that I just talked about was on the quiz. I just wanted to make sure that I did cover everything I wanted to for the exam. So please put everything away. Also, I'm going to put up a couple of extra questions that cover what we just talked about for you to practice with for the exam. So everything up to partial pressure is on the exam. You don't need to talk to put your things away. It's on Moodle. I think I said 6:15, but I'm doing another review at 4:30, so I don't remember exactly what time I put. But I will update that on Moodle, so that way that y'all know. So have everything away but your iClicker.